I think when we talk about deep space, I mean, the technical hurdles multiply compared to the low Earth orbit. And I really look at this as far as categories that I would, break this down into. And I see four major ones. Radiation protection. Next one is really propulsion beyond chemical rockets. Third one being life support and habitability. And lastly being in situ resource utilization. So I'll further break those down a little bit further right now. So really taking into consideration radiation protection. Once you leave Earth's magnetic shield, radiation becomes lethal over multi-year missions. So those cosmic rays, that solar particle events that can cause acute radiation sickness, organ damage, and increased cancer risk. So the current solutions really is the polyethyl-based shielding. So in the spacecraft, and that's advanced composites and potential use of lunar and the covered habitats. So it's really taking all into consideration, making sure that the humans and anyone else that are going into the atmosphere are protected. And then NASA is currently testing storm shelters inside Orion capsules as a near-term fix. From a futuristic standpoint, research is going into that magnetic shielding and plasma fields to mimic the Earth's atmosphere or magnetosphere.
Right. When you think about, we got radiation is just the one of the big drivers of, of what happens in space. Right. You got all these things you got to protect. The human body is not built for, right? And it's a cost driver to the business too, right? So that shielding alone adds weight, right? So weight is, as in any type of flight environment, weight costs money, right? Weight means you need more, you need better materials, you need things to be lighter, you need the shielding to happen. The storm shelters is that's tested out there, and they're already kind of used already on the space station out inside for Orion and other things. There's always a protective storm shelter type capability. Very, very expensive materials, but if you can solve this thing, right, it's not only help us from a technical perspective for people to stay out in space longer. It definitely helps, reduce the cost of going into deep space, which is one of those things, right? So what is one of the other ones, Rob? What is one of the others big killers?
Yeah, so I think the second big killer is really about propulsion beyond chemical rockets. So that chemical propulsion got us to the moon, but Mars missions need more efficient systems. So those efficient systems are really like the nuclear thermal propulsion. So DARPA and NASA's Dark Draco program is aiming for this first test to be in 2027, and that NTP, which is the nuclear thermal propulsion, could cut out Mars travel time from 9 months to 4 to 6 months. So that's a tremendous amount of time cut from a travel standpoint. So that, that's to your point, less cost, more advanced technology, less time in that atmosphere, that harsh atmospheres for humans. The second one being ion and Hall effect thrusters. So it's already being used in satellites for station keeping, scaling up for those deep space probes, but also NASA's Psyche mission uses solar electric propulsion. So that's electric is becoming a new way of thinking propulsion into space, which is great to see. And then lastly, I would hit on fusion concepts. So this is really still experimental, but private players like Helicity Space are exploring these future drives, which is, like you said, is futuristic, but it's really early in the development stage.
Yeah, it's all at the atomic stages, right? When you think about fusion and power and grabbing that, right? Either it's atomic fusion, it's hydrogen fusion, even nuclear fusion, to get you there faster from a propulsion perspective, right? Because it's all about that VBO, right? The velocity to get us out of there. Because you get off the ground, but you really got to sustain that for a while. And nuclear propulsion. Always, anytime you put the word nuclear in something, it's money, right? That's just how it is, because it's from a safety perspective, And what we're doing, even though it gives you the power it needs, there has to be the safety precautions that you got to take to get there and to make it work. And then, that Draco program right now, it's like funded like $500 million over the next 5 years.
Yeah.
And if it works, it can help with the logistics and give us shorter mission cycles and less life support. So again, the shorter the time to get to deep space, the shorter to get us to Mars that happens. But again, technically, you got to solve that propulsion problem to get there. What's another one that we got, Rob?
Yeah, the next one is the life support and habitability. So that's for Artemis and Mars. We need closed loop environmental control and life support system. So that's ECLSS. So that recycling 99% of water from urine, sweat, and condensation. That's absolutely useful. Regenerating oxygen via electrolysis, and also growing food in consumable and controlled habitats. So those are the main areas where we see reusable foods, reusable water, helpful in deep space. So radiation and microgravity also damage the human physiology. So they're also researching artificial gravity through rotating habitats, which is something I had never seen before. So in researching this, I was glad to see there's a lot of this being thought of. And that's like that advanced exercise regime. So it's like basically recreating your own gravity in outer space.
Yeah, that Eclipse is a thing I had the pleasure of working with, and seeing some of the guys work it when I was in my Collins life, working in the space systems business. Right, the Eclipse thing is real. It is what can we do to ensure that human life stays alive, right? As longer, because you got water needs, you got oxygen needs, you got organic feed needs, and then you got just the overall comfort too, right? So you can operate and be in that deep space environment, because it's just you're not coming back home for a while, right? You're not coming back to the planet at home for a while, so you got to make sure there's an environment there to deal with, right? So it's important. Mm-hmm. There's the business case there. All these systems will be dual use, right? You got that closed loop water recycling. Is not just for Mars, right? They're using it, also testing it to see the sustainability of that on Earth, right? And actually, you have a lot of investors that's dealing with those Eclipse type systems to do that here on the planet, right? And then also, you got to have something once you get to Mars. You got to maintain human life while you're on the planet of Mars, right?
It's all about survivability.
It's all about survivability, baby. And so, we have to really think through the capabilities and test those capabilities, and they have to test them, which is, I think, is cool about space exploration. They test the capabilities of what they need to the planet while they're in space before they get to the planet, right? and so, I mean, it's I know all the space nerds, when we get on our podcast, gonna have a lot to say about it. But for us people who are on the peripheral, who are really trying to learn it, the Eclipse thing is real. It's a real deal. It's a real deal. Right. What about this? Our last one that we want to share with the rest of the audience here.
Yeah. So that last one is about in situ resource utilization. So that's ISRU. And that's hauling everything from Earth. It's unsustainable in outer space and deep space. So the RSU means what's already there. So that lunar ice for fuel and water, that Regolith for 3D printing habitats, extracting oxygen directly from lunar soil. And, to that point, NASA's MOXIE program demo has already proved oxygen extraction from CO₂ on Mars, which is like hands down amazing work being done by that team. But like I said, we need to reutilize those resources, because not only is it going to take 4 to 6 months, ideally, from Earth to Mars, but also while you're there, it's going to take a while just to, do everything, do all the testing, all the experiments you need to do there, and then come back. So you're looking at years being in deep space at this point.
Right. What's driving this also from an in situ perspective, right, is there's ice. So, I mean, if there's ice, then there's water. There's some water source. If there's some water source, there's potentially some living sources there, some other living minerals that we can utilize while we're there on planet, right? And as well as, and so we need habitats to be created on there. That's happening. The lunar vehicles that we have that rolls and that rolls around, that's on there, that shows us there. And then the MOXIE demo that's just happened, getting that oxygen off that soil and getting that direct from the soil goes back to our last piece, of the eclipse piece. If I can get oxygen from the planet, then I don't have to utilize when I'm getting back in space to get back home, right? So I can utilize
Yep.
what's there. Also, which the quiet secret on this part is, there's also a lot of precious minerals and things like that that's on these that we've proven to be on these planets as well, which is also driving the economic impact. People wanting to invest to get these precious metals that's going to be needed is there, right? So, and the economics around that is crystal clear, right? You know, NASA says it's going to take about $10,000 per kilogram to launch material into space, right? And each kilo you don't spend on a launch is what save money, and whatever we can use there helps reduce the cost of me to get there. And then it also creates these commodity markets, which I was leading to, that's also dealing with the economics that can go around because of the precious metals that's on planet, right? So that's really cool to see what we got going on. So lot happening there.